You know, um, it is just incredibly frustrating when you're interacting with an AI and you suddenly realize it basically has the memory of a goldfish.
Oh, yeah. The classic blank slate problem.
Exactly. Like you spend 20 minutes explaining exactly what you need. You give it all this context. You establish a workflow. And
And then the next day you log back in and goes, hello, how can I help you today?
yes, every single conversation starts from absolute zero. It drives me crazy.
Right, because the intelligence is certainly there in the model, but there's zero continuity. I mean, the system just has no concept of looking at a prompt and realizing, wait, I've seen this before.
And that's exactly what we're exploring today for you, our listener. We got our hands on an internal technical architecture document for a platform called Heartbeat Agents.
Yeah, specifically a module titled Memory That Finds Itself.
Right. And our mission for this deep dive is to figure out how you give an AI a permanent, reliable memory without, building some fragile, overly complex tech stack, one that requires a dedicated team just to keep it from collapsing.
Which is super common, by the way. What's fascinating here is that historically, giving an AI long-term memory meant introducing massive infrastructure overhead.
Just a huge headache.
Totally. But this document isn't just about the fact that the Heartbeat Agent system remembers things perfectly. It's about how the system is specifically designed to survive and adapt when things inevitably break. It's really a masterclass in resilient architecture.
Okay, let's unpack this.
Yeah.
Because I'm genuinely excited about how this document bridges two totally different worlds.
Oh, the business side and the tech side.
Yeah. On one hand, you have the high-level strategy for the C-suite, the promise that the AI just remembers things instantly. But on the other hand, it goes incredibly deep into the hardcore engineering for the CTO.
We're talking deep database mechanics.
Exactly. And to understand how the AI actually searches this memory, we have to start with where all this memory actually lives. Which brings us to a surprisingly retro architectural choice.
Retro, but incredibly pragmatic. If you look at the typical AI setup today, a company usually runs their main database for all their standard application data, and then
They spit up a completely separate one.
right, a separate vector database on the side.
Like Pinecone or Weaviate,
Yeah.
these specialized databases built from the ground up just to hold the AI semantic memories, which are, basically just massive arrays of numbers.
Right. And the creators of Heartbeat Agents completely reject that dual database model. They use one single database for everything, PostgreSQL.
Which has been around for decades. I mean, it's the workhorse of the entire internet.
It really is. And they're utilizing a specific extension called pgvector.
Guy?
And this isn't just a bolt-on hack. pgvector adds native SQL operations right into the database, so it introduces native operators to compute cosine distance.
Which is how this system figures out how conceptually similar two memories are, right?
Exactly. And it allows them to use HNSW indexes.
Okay, HNSW. Hierarchical Navigable Small World Indexes. That sounds like, I don't know, a piece of alien technology from a sci-fi novel.
Yeah.
Let's break that down for the listener, because the document goes deep into the parameters.
Yeah, it gets pretty technical.
It does. They use an M value of 16 and an F construction of 200. What does it actually mean in plain English?
Think of HNSW like playing the 6 Degrees of Kevin Bacon game, but for data.
Okay, I like that.
When you have millions of memories, you can't have the AI checked every single one sequentially to find a match. That would take way too long.
Right.
Instead, HNSW creates a massive web of shortcuts between concepts.
So it's building a map of associations.
Yes. That F value of 16 means every time a new memory is added, the system connects it to 16 other related memories, building out the graph.
Ah, okay.
And the F construction of 200 is basically the search breadth. It tells the database to look at 200 potential candidates while finding the absolute best spot to place this new memory in the web. Yeah, so the system builds this map of shortcuts so it can skip across millions of data points in milliseconds. And crucially, they build this index concurrently.
Which means they don't lock up the database table while it's building. The app keeps running for the user.
Exactly.
Looking at this, using a completely separate vector database for AI memory feels a bit like towing a U-Haul trailer behind your car everywhere you drive, just in case you happen to buy a couch that day.
That is a great way to put it.
It's an extra point of failure. It adds latency because you have to pass data back and forth, and it's an extra security risk you have to monitor constantly. Realizing you could just use PostgreSQL with pgvector is like realizing your daily driver SUV already has foldable seats in the back. You didn't need the trailer, you just needed to pull a lever.
If we connect this to the bigger picture, that foldable seat analogy is exactly what the C-suite and the CTO care about. Having one database means you only have one backup strategy to manage.
Oh, that's huge.
You only have one network boundary to secure. There are no cross-service API calls trying to sync your user's business data with your AI's memory data.
You just query it all together.
Right. You can just write a standard SQL Join query to connect an agent's memory vector directly with their standard user profile. It simplifies the entire stack.
It sounds incredibly clean. But here's the catch. Keeping everything in one single database creates a massive structural problem if you ever want to switch which AI model you're using.
Yes, the shape problem.
Different AI companies output their memory vectors in entirely different shapes. How do you fit wildly different shapes of data into one single rigid database column?
This is where the engineering gets really clever. The document outlines a database column defined as vector 1536.
Okay.
That number, 1536, is the strict dimensional size of the column. It cannot be anything else.
But the document lists 7 totally different embedding providers that the system supports. You've got the massive cloud models like OpenAI and Google Gemini, down to free local ones you can run entirely on your laptop, like Llama.
And they all spit out different sizes of data.
Right. OpenAI's text embedding 3 small model outputs exactly 1,536 dimensions, so that fits the column perfectly. But Hugging Face's all-minimal LM-L6 V2 model is only 368 dimensions.
And the Llama option, which uses nomic embed text, outputs 768 dimensions.
So wait, if my database column is strictly locked at 1,536 dimensions, how on earth do we fit a 384-dimension Hugging Face memory in there? Do we stretch the numbers out? Doesn't alter the data like that completely ruin the semantic meaning of the memory?
You'd think so, but they use a brilliant mathematical trick. In their code, there's a function called pad-to storage.
Pad to storage.
Yeah. When a vector is shorter than 1,536 dimensions, the system simply adds zeros to the end of it until it reaches the required length. It zero pads the data.
Just literally tagging zeros onto the end of the string. Doesn't that move the coordinates and scramble the AI's memory?
Well, let's look at the geometry behind it. Adding zeros to the end of a vector does not change the angle between two vectors from that same provider.
Oh, I see.
The core mechanism used to find matching memories is cosine similarity, which measures the angle between these data points in high-dimensional space from their origin. Because those new dimensions are just empty space, the zeros don't shift the angle.
The angle stays exactly the same.
Exactly. The semantic relationship between the memories is perfectly preserved.
Wow. Because the relationship between the memories hasn't changed relative to each other, the math still works. So you get to keep your perfectly uniform database column, but you can hot swap your AI provider whenever you want without breaking the storage architecture.
Precisely. If a better model comes out tomorrow, or if a provider suddenly triples their API costs, you just switch your settings.
And it doesn't break.
No, the system starts zero padding the new provider's vectors, and a background task slowly re-embeds your old memories with the new model so everything stays compatible. No data migration, no downtime.
So padding the data solves the storage problem perfectly. But it creates a massive needle in a haystack problem. You got all these perfectly padded memories shoved into one giant database column. How on earth does the AI find the exact memory it needs in under a second?
Right, because memory is useless if you can't recall it instantly.
Exactly.
This brings us to their hybrid search mechanism. It's really the technical centerpiece of the whole system. The platform doesn't just rely on one way of searching. It basically has 3 brains working at the exact same time.
3 brains.
Yeah, it runs 3 parallel search strategies, merges all the results together using a standard SQL union command, and then ranks the top 100 candidates.
Break down those 3 brains for me. Okay, so the first is vector search, which is this semantic layer. It uses that HNSW shortcut map we talked about to find the top 50 conceptual matches.
Okay, so concepts. Right. If the agent searches its memory for send notification, the vector search is smart enough to find a skill called post Slack alert. Even though those 2 phrases share absolutely 0 matching words, it understands the conceptual vibe of the request.
But semantic search isn't perfect, right? Sometimes you don't want a vibe, you want a specific thing.
Which is why strategy 2 is full text search. This is the linguistic layer. It uses PostgreSQL's built-in text engine, the GIN index, to tokenize and stem words.
Stemming, like finding the root.
Exactly. So if you search the word running, it mathematically boils that down to its root and matches it with the word run.
Got it. And the third brain?
Finally, strategy 3 is substring match. This is the exact literal layer. It uses I-like pattern matching to find the top 20 exact phrase matches character for character.
It's like looking for a very specific book in a massive, sprawling library. Strategy 1, the vector search, is walking up to the librarian and saying, hey, I'm looking for books with a really spooky, isolated vibe. Strategy 2, the full text search, is going to the card catalog and looking up the root words haunt and hotel. But strategy 3, the substring match, is walking in and demanding the exact phrase, all work and no play.
I love that.
You really need all three of those strategies firing at the same time to guarantee you're going to find a copy of The Shining.
That analogy captures the necessity of the hybrid model perfectly, but merging those three streams of results creates a new challenge. How do you rank the top 100 candidates so the absolute best memory floats to the top?
Right, because you just dumped three different types of search results into one bucket.
Exactly. They factor in two really elegant mathematical metrics, quality and recency.
Let's talk about that quality score, because the document says they use something called Laplace smoothing. That sounds like a skincare routine for data. Break that down for me. I assume they aren't just looking at a raw success rate.
No, a raw success rate is actually quite dangerous for an AI system. Let's say you have a brand new memory or skill that the AI just learned. It has 0 executions and 0 successes. If you just do simple division, its quality score is 0. The AI will never use it because it ranks too low.
You never get the chance.
Exactly. Laplace smoothing fixes this by tweaking the formula. Instead of successes divided by executions, the formula is successes plus 1 divided by executions plus 2.
Why the plus 1 and plus 2?
It acts as an artificial anchor. With 0 successes and 0 executions, the math becomes 1 divided by 2. So a brand new memory automatically starts with a 50% quality score.
Oh, wow. It gives new ideas a fair chance to be used.
Exactly. Furthermore, if a skill works perfectly 10 times but fails on the 11th due to a random glitch, this formula ensures that one single failure doesn't drag a 100% score down dramatically and completely destroy its ranking. It smooths out the volatility.
That is incredibly smart. And then there's the recency score, which uses hyperbolic decay. I'm assuming this is how the AI knows to prioritize something we talked about yesterday over something we talked about 6 months ago.
Yes. The formula takes the number of seconds since the memory was last used and divides it by 86,400.
Which is the number of seconds in a single day.
Right. The resulting math means a memory access today gets a score very close to 1.0. But a memory untouched for a week mathematically decays down to around 0.125.
It guarantees the AI prioritizes fresh, relevant context without permanently deleting the old stuff.
Precisely.
Hearing all this, 3 parallel search strategies, semantic vector math, full-text tokenizing, Laplace smoothing, hyperbolic decay. This sounds incredibly heavy. We're relying on all this math, plus external APIs like OpenAI to process the vectors. What happens if the API suddenly crashes? Does the agent just freeze up?
That is the million-dollar question.
Does the whole application lock up waiting for a response?
This brings us to one of the most critical architectural philosophies in this document, the art of failing gracefully. Most modern tech stacks are incredibly brittle. If one microservice goes down, the whole chain shatters.
It's just cascading failures everywhere.
Right. But Heartbeat Agents has 4 distinct fallback layers specifically designed so the system never fails the user, even during an outage.
Here's where it gets really interesting. Let's walk through those fallback layers.
Yeah.
If the OpenAI API just completely crashes at runtime, how does the database not throw a massive error?
Layers 1 and 2 handle the API failures directly. If the embedding provider fails, the system just catches the error silently. Yeah. The query embedding becomes a none value. The vector score smoothly drops to 0, and the SQL query simply excludes the semantic search.
Wow.
The hybrid search instantly falls back to scoring based solely on text matching, quality, and recency. The user has no idea the API just crashed, the search still completes, and the AI gets its memory.
And then there's layer 3, which implements a strict 1.0 second timeout on memory injection. When the AI is getting ready to run a task, it searches for memories to help it. If the database is under load and that search takes longer than 1 single second, the timeout fires, and the agent just runs its task without the injected context. Okay, wait. I have to push back on this. Dropping the memory entirely after just 1 second. Isn't that dangerous? Shouldn't an AI wait to make sure it has all the facts before it starts acting?
This raises an important question about how we view AI architecture.
Yeah.
The document states explicitly, memory is an enhancement, not a load-bearing wall.
Wow.
Think about it from a user experience perspective. An AI that acts slightly forgetful, maybe it asks you for a detail you provided last week, but still ultimately completes its primary task, is infinitely better than an AI that crashes entirely and throws a 500 error because of a minor database hiccup.
Reliability over perfection. I like that. And layer 4 applies to storing new memories. Normally, the system checks for duplicate memories using vector similarity before saving, but if the vector API is offline, deduplication is skipped entirely.
Storing a duplicate piece of data is vastly preferable to losing that data entirely. They prioritize data retention over database cleanliness during an outage.
You can always clean up the duplicates later when the system is back online. Okay, let's say the API is up, the math is working perfectly, and the AI finds 50 incredibly relevant memories. This creates a brand new problem. Even a state-of-the-art AI has a limited context window, a strict limit on how many words it can hold in its active brain at one time.
Yes, the context limit is a huge bottleneck.
If my AI remembers 5,000 interactions we've had, feeding all of that back into its prompt for every single task is going to crash the system and cost an absolute fortune in token limits. How do they stop it from hoarding?
You're talking about the transition from mere storage to actual memory intelligence. It requires aggressive curation. First, they enforce a strict injection limit. The memories injected into the agent's prompt are capped at exactly 10% of the agent's maximum token allocation.
With a hard ceiling of 3,000 tokens,
Right.
So it physically cannot be overwhelmed by its own nostalgia. But how does the AI mathematically ensure it's getting a useful, diverse mix of memories in those 3,000 tokens, rather than just the top 10 results that all say the exact same thing?
To ensure those tokens are actually useful, they use an algorithm called MMR, or Maximal Marginal Relevance.
MMR. Okay.
Out of the top 20 search results, it selects only 12 memories to inject. It iteratively picks memories by balancing their relevance score against how similar they are to the memories it has already picked for the prompt.
Okay, so it compares the new ones to the ones already in the bucket.
Exactly. And it measures that similarity using Jacquard distance.
Jacquard distance.
Yeah.
That's like looking at the overlap in a Venn diagram of words.
You got it. It's a highly efficient way to measure the overlap between two sets of text without needing another expensive vector API call.
Nice.
So by mathematically punishing memories that share too many words with what's already been selected, the algorithm actively enforces diversity in the AI's thought process.
It's exactly like putting together a dinner party guest list. You want relevance, you want smart, interesting people, but you don't want to invite 12 people who all have the exact same job, live in the same neighborhood, and have the exact same opinions.
Right, that would be terrible.
That's high relevance, but way too much similarity. It makes for a boring party. You want a diverse mix of people who bring different, unique perspectives to the table. That's what MMR does for the AI's prompt.
The dinner party analogy captures it perfectly, but the system doesn't stop at just curating the prompt. It also utilizes a background consolidation task. Periodically, the system scans the database and clusters memories that have a cosine similarity of 0.82 or higher.
2x2, okay.
If it finds a cluster of 3 or more highly similar memories, it actually sends them to a large language model to be merged into a single, concise summary.
It cleans house while we aren't looking.
It's essentially an artificial form of sleep. Think about human biology. During REM sleep, our brains consolidate the day's events, pruning away redundant information and integrating new lessons into long-term structures.
That is wild.
This system is doing the exact same thing mathematically. It organizes its thoughts in the background so it's fresh and optimized for the next day's tasks.
And to prevent endless bloat over the years, there's a hard cap 500 memories per agent. If an agent hits 501, the lowest importance memories are pruned permanently. Plus, whenever a new memory is created, it's instantly deduplicated if it hits a 0.88 similarity threshold, or 0.92 if you explicitly command it to remember something.
It has to stay lean.
So what does this all mean? We started this deep dive looking at a technical document about database architecture. But the core takeaway here is that true architectural elegance isn't about endlessly adding new features or bolting on new vector databases just because everyone else is doing it.
Definitely not.
Elegance is designing a system that works perfectly without the feature and simply gets smarter when you turn it on. Zero required configuration, one single database, and absolutely no vendor lock-in.
It's a profound shift from building brittle tech stacks to building resilient, organic feeling systems.
And to you, our listener, I think this really validates that feeling of information overload we all struggle with daily. If even a state-of-the-art AI system has to actively prune its memory, strictly deduplicate its thoughts, and limit its daily intake just to stay smart and functional, maybe we shouldn't feel so bad when we can't remember every single thing we read online.
It's a striking parallel. We spend so much time and engineering effort worrying about how to give AI limitless permanent memory. But looking closely at this architecture, the real secret to AI intelligence isn't its ability to remember everything. It's its mathematically programmed ability to decide what to forget.
Yeah.
If an advanced AI requires a strict 500 memory limit and constant daily pruning just to remain useful, what does that say about our own modern human habits of digital hoarding? Saving thousands of unread articles, taking thousands of photos we never sort, hoarding bookmarks we never look at again. Maybe true intelligence requires letting go of the noise.
That's something to chew on next time you leave 50 tabs open in your browser. Thank you so much for joining us on this deep dive. Next time you're talking to an AI and it actually remembers what you said yesterday, you'll know exactly how many database queries and mathematical tricks it took just to cure it of its goldfish memory. Catch you next time.